All right, we're back here, calculus folks, with the last couple of examples on the first day of shortcuts called derivatives and tangents. You're going to need to do all the work on separate paper. I'm going to try and squish it in right here. But let's get into it. We've got a graph of a function. It's a polynomial function. And we want to determine the equation of the tangent at x equals minus 1. So at x equals minus 1, let's see, would be right about there. Oops. That's definitely not the tangent, but something like that might be. So what's the equation? Well, we're going to come up with it. Notice that before today, finding the equation of a tangent was a huge pain in the butt because we would have had to figure out the derivative from first principles, right? Where a is minus 1 and so on and so on and so on, and the work was long and difficult, but not so bad now. Because now the derivative gives the slope of the tangent, and the derivative is easy to get, right? 12x squared plus 6x, and the constant disappears. So, and we want to find the equation of the tangent at x equals minus 1. Well, that's going to be this will give the slope, right? This was kind of the advantage of calculating the derivative function, is that we could find the slope at any point we wanted to. And you pound that into a calculator, excuse my handwriting there, and you get 6. So therefore, the slope of the tangent is 6. And then I can use good old y equals mx plus b, where m is 6, x is minus 1. Now what's y? Y is f at minus 1. Put that in the original equation, you get, what is f at minus 1? Minus 6. All right, 4. Just put it into the original equation. Having pen problems here. There we go, just slow things down a little bit. And what do I get? I get b is 0? So my tangent was a little bit off. This tangent should have went through 0. I wonder if it will look better if I make it go through 0. Does that look like a better tangent? Oh yeah, that's way better. Way better. So the equation of the tangent is y equals 6x. I'd say y equals 6x is the required equation. Okay, it says determine other points on the graph with tangents parallel to the line found in A. Well, how are we going to do this? Well, notice I could just sort of, where's it going to be? Where's it going to be? Well, and this is a guessing thing, right? We can do better than that. It looks like it's going to be right about there, maybe at x equals 1, maybe around there. But let's do this real grown-up boys and girls style. So what do we want? We want f prime at x to be 6, right? Well, f prime at x is that function. So where is 12x squared plus 6x? Is it plus 6x or minus 6x? Plus 6x equal to 6, because that's where we'll have the same slope. The slope of the tangent will be the same. Well, quadratic equation. I'm going to divide everything by 6, simplify it a little bit. Factor. And I get 2x minus 1 and x plus 1. That gives me the 2x values. This is the one we already knew, right? And x equals a half. Now I'm interested. X equals a half. Ooh. And that's what it was. I was reading it as 1, but it's actually at a half, so that's looks good on our graph. So is parallel or has a slope of 6 at, and I know negative 1, negative 6 was, this was from part A, and the new one is a half, and I don't really care about what the y value is. You can punch that into a calculator and do that on your own time. In the privacy of your own home, you can do whatever you like, I suppose. And there we go. Done. Find the points on f at x that have horizontal tangents. Okay, so horizontal tangents are like this, right? Horizontal tangents. Slope is what? What's the slope for horizontal tangent? It's 0, isn't it? Right? This is slope is 0. We want f prime at x to be equal to 0. And just before we go ahead and do this, let me tell you how awesome this is, because you remember from functions, when we were drawing graphs of polynomial functions, we didn't know how far the bump should go up, right? We didn't know where these maximums and minimums would occur. And this is going to be awesome because we'll know where the bumps go, or how far up the minimums and maximums are. So this is the start of something beautiful. All right, let's get into it. We have 12x squared plus 6x, and that's equal to 0 for a horizontal tangent. And factor. Or formula, but I wouldn't use formula. X equals 0, and here x equals negative a half. And again, I don't really care about the y values too much because I want to get to through this example sometime today. So therefore, f at x has a horizontal tangent pen troubles here at 0 and f at 0, I suppose. That one's actually not that difficult to calculate. I think f at 0 is just the constant part, which is negative 5, but oh well. If we're going to be lazy, we're going to be lazy. And negative a half f at minus a half. Whatever the y value is if I pounded that back in there. Done. Lovely. So that's going to be good when we get into curve sketching. We'll know where the minimums and maximums occurs by setting the derivative function equal to 0. That's going to be awesome. Example 3. Last example of the day. Determine the equation of the tangents to the curve that pass through the point negative 1 and negative 6. Before we get into this, just a little sketch here, just so we have an idea of what's going to happen. You know, this is a parabola, and it's up a couple, right? This is going to look something like this. Here's 2. It's going to look something like this, right? Maybe a little less wobbly, I hope. And then where's negative 1, negative 6? Negative 1, negative 6 is here, say. And so I want to find where the tangents are, right? And I can see there's probably a couple of them there. That's not a great diagram, but we get an idea. There's going to maybe be two, right? Well, how is this going to work? Well, we know what the derivative has to be. Let's get a decent sized pen here. The derivative, which gives me the slope of the tangent, is 2x, right? And so this point, and we think there's going to be two of them, but we don't know where they are really. That was just a guess. It was a bad diagram. Is going to be this point. We're not sure what the x value. I'm going to call it a, though. It's some value that we haven't found yet. A, and notice a squared plus 2 is the y coordinate of that one. But I also know the slope of this line has to be equal to not 2x, but 2a, right? Right? The slope of this line is 2 times a, because a is the value of the function at that. So here, the slope, which is just y2 minus y1 over x2 minus x1 has got to be equal to 2a. And then I can simplify this. Cross multiply. Get everything on one side. A squared plus 2a minus 8. That factors. Doesn't it always factor? So I get a is minus 4 and a is 2. So then we got to still calculate the equation of the tangents. Notice for a is minus 4, then the slope is 2a, right? Which is minus 8. X plus b, but what's the equation of the point? With a is minus 4, x coordinate is minus 4, and then minus 4 squared plus 2 gives me the point minus 4 and 18. And then 32, subtract 32 from both sides, b is minus 14, unless I've made an arithmetic error. Minus 8x minus 14 is one equation. Similarly, that's the first one, is the required equation. A equals 2, I'm just going to go dot, 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 gives you the equation of the line y equals 4x and b is minus 2. I think. Okay, that's it. And lots of good stuff in the homework that are similar to that. That was a lot. That last problem was a good one. Good thinking problem. There was a thinking problem like that actually in chapter 1 if you you tried that one. Okay, good luck with the homework.